On a clear winter night, if you step outside and look toward the constellation Orion, you will find it without much difficulty. 3 stars in a neat diagonal line, the famous belt. Below them, a fainter trio suggesting a sword. Above and to the left of the belt, a star that does not look quite like the others. It is not the sharp, blue-white of most bright stars. It is warm, ruddy, the color of embers seen through smoke, or of a sunset caught at just the right moment before it fades. That star is Betelgeuse. It has been there, in that same position, carrying that same warm glow, for every human night sky in recorded history. Ancient Egyptians saw it. Greek astronomers named the constellation around it. Medieval Arab scholars gave it the name we still use today, derived from the Arabic for the shoulder of the Great One. For thousands of years, it has been one of the most recognizable stars in the night sky, familiar, constant, reassuring in its presence. And yet, in the past several years, Betelgeuse has been doing something unexpected, something that has drawn the attention of astronomers around the world, generated hundreds of scientific papers, and sparked a quiet, sustained excitement in observatories and research institutes across the planet. Betelgeuse is changing, dimming, brightening, behaving in ways that do not fit neatly into the patterns we expected. And beneath all of that observable change lies a deeper truth that scientists have known for some time. A truth about the nature of this star, its age, and what its future holds. Betelgeuse is dying. Not today. Perhaps not for 100,000 years. Perhaps sooner. We do not know precisely when. And that uncertainty, combined with its extraordinary proximity, its remarkable brightness, and the sheer spectacle of what its death will involve, is exactly why scientists are paying such close attention to what it is doing right now. Tonight, we explore Betelgeuse, slowly, gently, with wonder, and with patience. We will learn what it is, how it came to be, why it behaves as it does, and what will happen when it finally reaches the end of its extraordinary life. There is no urgency in this story, only depth. As we begin our journey with Betelgeuse, let us first understand what kind of star we are dealing with, because Betelgeuse is not merely a large star. It belongs to a category so extreme that ordinary language struggles to do it justice. Betelgeuse is a red supergiant. It is one of the largest stars known in the observable universe by physical radius. Estimates of its size have varied over the years as measurement techniques have improved, but current best estimates place its diameter at somewhere between approximately 700 and 900 times the diameter of our Sun. Let us sit with that for a moment. Our Sun has a diameter of approximately 1.4 million kilometers. If Betelgeuse were placed at the center of our solar system, where the Sun currently resides, its surface would extend outward past the orbit of Mars. Some estimates suggest it might reach nearly to the orbit of Jupiter. The entire inner solar system, Mercury, Venus, Earth, Mars, would be swallowed within the body of the star. Earth itself, in this scenario, would not merely be consumed. It would be deep inside the star, embedded in the outer layers of stellar plasma, surrounded on all sides by the roiling, convecting surface of a dying giant. And yet, despite its immense volume, a volume roughly 300 million times that of our Sun, Betelgeuse is not proportionally more massive. It contains only somewhere between 10 and 20 times the mass of our Sun. The star is, in a sense, puffed up, an enormous balloon of relatively low-density gas, extended far beyond what its mass alone would suggest. This is the nature of red supergiants. They are stars in a late stage of their lives, stars that have exhausted their hydrogen fuel in their cores and expanded enormously as their internal structure adjusts to new sources of energy. Betelgeuse is not large because it formed large. It is large because it is old. Let us take a moment to understand where Betelgeuse sits in relation to us, because its distance carries profound implications for both what we observe and what we need not fear. Betelgeuse is located in the direction of the constellation Orion, at a distance that has been revised multiple times as measurement techniques have improved. Current estimates, informed by data from the Hipparcos satellite and more recent interferometric measurements, place it at approximately 500 to 700 light-years from Earth. A commonly cited figure is around 700 light-years, though the precise distance carries some uncertainty. 700 light-years. That means the light we see from Betelgeuse tonight, the warm, ruddy glow that catches the eye on a winter evening, left that star approximately 700 years ago. When that light departed Betelgeuse, the 14th century was just beginning on Earth. The Black Death had not yet swept across Europe. Dante Alighieri was still alive. Whatever Betelgeuse looks like right now, in this present cosmic moment, we will not know for another 700 years. We are always observing it as it was, never as it is. The star we watch in the sky tonight is a 700-year-old image, preserved in the amber of traveling light. This temporal displacement is important to keep in mind throughout our exploration tonight. When we speak of Betelgeuse dimming, brightening, or changing, we are speaking of changes that occurred centuries ago. We are observing history. At 700 light-years, Betelgeuse is also distant enough that when it eventually explodes, when it ends its life in a supernova, the radiation it releases will not pose any meaningful threat to life on Earth. It is close enough to be spectacular, far enough to be safe. That distance is, in its way, a gift. As we continue, let us trace Betelgeuse's history to understand how a star arrives at the extraordinary state it now occupies. All stars begin the same way. A cloud of gas and dust, primarily hydrogen, with some helium and trace amounts of heavier elements, begins to collapse under its own gravity. As it collapses, it heats. Pressure builds at the center, and when the temperature at the core reaches approximately 10 million degrees Celsius, nuclear fusion ignites. Hydrogen nuclei, protons, begin to fuse together, forming helium and releasing energy. That energy provides the outward pressure that balances gravity's inward pull. The star reaches equilibrium, a long, stable period of hydrogen burning that can last billions of years. For a star like our Sun, this stable period, called the main sequence, lasts approximately 10 billion years. Our Sun is currently about halfway through its main sequence lifetime, but Betelgeuse was born much more massive than our Sun, and mass is destiny in stellar physics. More massive stars burn their hydrogen fuel much more rapidly. The greater gravitational pressure at their cores drives higher temperatures and faster fusion rates. A star 10 to 20 times the mass of our Sun might remain on the main sequence for only 8 to 10 million years, 1,000 times shorter than the Sun's main sequence lifetime. Betelgeuse is estimated to be somewhere between 8 and 10 million years old. On a cosmic timescale, this is extremely young. Our solar system is 4.5 billion years old, roughly 500 times older than Betelgeuse. And yet Betelgeuse is already approaching the end of its life, while our Sun is still comfortably middle-aged. It burned bright and fast. And now, having exhausted the hydrogen in its core, it has entered the final chapters of its existence, swelling into the red supergiant we observe today. Consider the internal structure of Betelgeuse as it exists today, because it is a layered, complex object, very different from the relatively simple hydrogen-burning stars of the main sequence. When a massive star exhausts the hydrogen in its core, gravity wins, temporarily. The core contracts, heats further, and at the higher temperature, a new fuel ignites. Helium, the ash of hydrogen burning, begins to fuse, combining to form carbon and oxygen. Helium burning is faster and more energetic than hydrogen burning. While helium fusion proceeds in the core, hydrogen continues to burn in a shell surrounding the core. The outer layers of the star expand enormously. The star puffs up into the red giant or supergiant we observe. As helium is exhausted in turn, the same process repeats. The core contracts again. Carbon ignites, then neon, then oxygen, then silicon. Each stage is hotter, faster, and shorter-lived than the one before. The result is a layered structure, like a cosmic onion. At the center, the most recently ignited fuel burns in a core. Around it, successive shells of earlier fuels continue burning. Hydrogen burns in an outer shell, helium in the next shell inward, carbon inside that, and so on, down to the innermost core. In Betelgeuse, this process is well advanced. The star is believed to be in the late stages of its nuclear burning sequence, perhaps in the phase of carbon or neon burning in its core, with shells of earlier fusion products surrounding it. Each stage of this nested burning is producing increasingly heavy elements, the building blocks of chemistry, the raw material of planets, and ultimately of life. And each stage is consuming its fuel faster than the one before. The end is not imminent on a human timescale, but in stellar terms, it is approaching. As we continue our exploration of Betelgeuse, we arrive at the event that brought it to widespread public attention in recent years, the phenomenon astronomers have called the Great Dimming. For much of recorded history, Betelgeuse has been one of the 10 brightest stars in the night sky. Astronomers assign stars a numerical brightness value called magnitude. Lower numbers indicate brighter objects. Betelgeuse typically sits at around magnitude 0.5, making it clearly visible and quite bright, even in moderately light-polluted skies. But beginning in late 2019, something changed. Betelgeuse began to dim. Not dramatically at first, but progressively, measurably, and in a way that exceeded the range of its normal variability. By February 2020, Betelgeuse had faded to approximately magnitude 1.6, roughly 2.5 times dimmer than its typical brightness. For a star that had been reliably bright for millennia, this was a significant and noticeable change. It had dropped out of the top 10 brightest stars in the sky for the first time in recorded memory. Astronomers around the world turned their instruments toward it. Papers were written, hypotheses were proposed, and in the popular press, one question began to circulate with increasing frequency. Was Betelgeuse about to go supernova? The answer, as we now understand it, is almost certainly not, at least not as a direct consequence of the Great Dimming. But the dimming itself turned out to be scientifically fascinating for entirely different reasons. It revealed something about the surface activity of this extraordinary star that astronomers had not previously observed at such scale. And it opened a window into the dynamic, turbulent nature of a red supergiant in the final stages of its stellar life. As the astronomical community analyzed what had caused the Great Dimming, two explanations emerged, and remarkably, both turned out to be partially correct. The first hypothesis involved a large cool region on Betelgeuse's surface, something like a star spot, analogous to the sunspots that appear on our own sun, but vastly larger. Sunspots form where strong magnetic fields suppress the convective transport of heat, creating cooler, darker patches. On Betelgeuse, a similar process, but at a far grander scale, could create a cool region large enough to noticeably reduce the star's total brightness. The second hypothesis was more dramatic. It proposed that a large mass ejection, a burst of material from Betelgeuse's surface, had cooled as it traveled outward and condensed into dust. A cloud of newly formed dust, positioned between us and the star's surface, could absorb and scatter Betelgeuse's light before it reached us, causing an apparent dimming. Subsequent observations, including detailed analysis from the Hubble Space Telescope and several ground-based observatories, provided evidence for both mechanisms, working in combination. It appears that a large convective cell on Betelgeuse's surface, a vast bubble of hot plasma rising from the interior, erupted, ejecting a significant mass of material into the surrounding space. That material, once it traveled far enough from the star's intense heat, cooled and condensed into a cloud of silicate dust. Meanwhile, the disrupted surface region having lost energy in the eruption, was temporarily cooler than the surrounding photosphere. The dimming was caused by a combination of a cool surface patch and a dust cloud. Together, they produced the most significant observed dimming event in Betelgeuse's recorded history. The star was not dying in that moment. It was simply exhaling. Let us follow what happened to Betelgeuse in the months and years after the Great Dimming, because the story did not end with the star simply returning to normal. By April 2020, Betelgeuse had begun to brighten again. By late 2020 and into 2021, it had recovered to near its historical average brightness, and then continued to brighten further. By early 2023, Betelgeuse was observed at exceptional brightness, significantly brighter than its historical average. At times, it became one of the brightest stars in the sky, rivaling or surpassing stars it had not outshone in recorded observation. This post-dimming brightening was itself remarkable and not immediately understood. Was it simply the star returning to normal variability after an unusual disruption? Was something deeper happening in its interior? Some change in the nuclear burning that was producing more energy output? Astronomers proposed that the Great Dimming had disrupted Betelgeuse's normal pulsation cycle, the regular brightening and dimming driven by oscillations in the star's outer layers, and that the star was taking time to re-establish its rhythms. The subsequent unusual brightness might be a consequence of that disruption, with the star overcorrecting in a sense after the dimming event. There is also a longer-term cycle in Betelgeuse's variability, a roughly 2,000 to 2,400-day period of brightening and dimming, in addition to the shorter approximately 400-day cycle most commonly observed. The star's recent brightness peak may partly reflect the high point of this longer cycle. What all of this tells astronomers is that Betelgeuse is a dynamic, complex, actively variable object, not a static light in the sky, but a living star in the truest sense, constantly changing, constantly revealing new aspects of its nature. It is speaking to us in the language of light, and we are learning, slowly, to understand what it is saying. As we journey deeper into our understanding of Betelgeuse tonight, let us consider what its surface is actually like, because it is one of the most extreme and extraordinary surfaces in the known universe. Betelgeuse is among the very few stars that can be resolved as a disk rather than a point of light, even through ground-based telescopes. Most stars, even the largest ones, appear as mere points of light because of their immense distance. But Betelgeuse, with its enormous size and relative proximity, presents a disk large enough to be imaged directly using interferometric techniques. Those images have revealed a surface in constant dramatic motion. The surface of Betelgeuse is not the relatively orderly, slowly evolving surface of a star like our Sun. It is dominated by enormous convective cells, vast bubbles of hot plasma rising from the interior, releasing energy, cooling, and sinking back down. On our Sun, these convective cells, called granules, are typically about 1,000 kilometers across and last for about 10 minutes. On Betelgeuse, a single convective cell can be larger than the entire Sun. It can persist for months or years. The scale of the convective activity is, by any solar standard, almost incomprehensible. These giant convective cells are responsible for the irregular, somewhat mottled appearance that high-resolution images of Betelgeuse reveal. Bright regions where hot plasma is rising, darker regions where cooled plasma is sinking. The surface is a constantly churning, constantly shifting landscape of plasma at temperatures of around 3,000 to 4,000 degrees Celsius, cooler than our Sun's surface, which is why Betelgeuse appears red rather than yellow-white. Imagine standing at the edge of such a surface, a horizon that curves away in every direction. Plasma the size of continents rising and falling, columns of material being ejected into space, a sky not of stars, but of the star itself, extending in all directions, without limit. It is, in a word, sublime. Deep within our understanding of Betelgeuse lies a process that is slowly, but continuously changing the star. The loss of mass through a powerful stellar wind. All stars lose some mass through stellar winds, streams of charged particles ejected from the stellar surface by radiation pressure and other mechanisms. Our Sun loses roughly 1/1,000,000th of its mass every 100 million years through its solar wind. By stellar standards, this is modest. Betelgeuse is far less conservative. Red supergiants like Betelgeuse are among the most prolific mass-losing stars known. Betelgeuse is estimated to be losing mass at a rate roughly 10 million times higher than the Sun, shedding something in the range of one solar mass every 100,000 years, or perhaps more during particularly active periods. Over its lifetime, Betelgeuse has lost a significant fraction of its original mass. What began as a star perhaps 20 times the mass of our Sun has been gradually depleted, and the material it has shed forms an extensive circumstellar envelope surrounding the star. This envelope, a vast, complex structure of gas and dust extending far beyond the star's visible surface, has been studied extensively. It shows evidence of previous mass ejection events, of asymmetric outflows, of arcs and shells of material scattered by thousands of years of stellar wind activity. The great dimming of 2019 and 2020 was, in part, a manifestation of this mass loss process, a more vigorous than usual ejection of material that temporarily obscured part of the star's light. This ongoing mass loss is part of the story of how Betelgeuse will end its life. When the star eventually exhausts all its nuclear fuel and the core collapses in a supernova, the explosion will propagate through this circumstellar envelope, illuminating it, energizing it, and creating a spectacular nebula that will glow for thousands of years. The material Betelgeuse is shedding today will be the stage set for its own death. As we continue our exploration tonight, let us examine one of the most fascinating aspects of Betelgeuse's behavior, its regular pulsations. Because Betelgeuse does not shine with a constant, steady light, it breathes. Stars like Betelgeuse, red supergiants and other evolved giant stars, undergo oscillations in their outer layers. These oscillations are driven by complex interactions between the star's luminosity, its opacity to radiation, and the dynamics of its outer envelope. In a simplistic picture, you can imagine the outer layers of the star alternately expanding and contracting, like the chest of a sleeping giant, rising and falling in slow, regular rhythm. As the layers expand, the star cools slightly and reddens. As they contract back, the star heats and brightens. Betelgeuse has been observed to pulsate on several timescales simultaneously. The most prominent is a period of approximately 430 days, a cycle of brightening and dimming that repeats roughly every 14 months. Observers monitoring Betelgeuse over decades have tracked this cycle with considerable precision. There is also a longer semi-regular cycle of approximately 2,000 to 2,400 days, a slower oscillation driven by different physical mechanisms, possibly related to large-scale convective motions deep within the star's envelope. And there are shorter period oscillations as well, complex overlapping rhythms that combine to produce the irregular variability that characterizes Betelgeuse's light curve when observed in detail. The great dimming of 2019 and 2020 appears to have disrupted the star's normal pulsation pattern, particularly the 430-day cycle. In the aftermath of the dimming, the cycle appeared to reset or shift, and subsequent observations suggested a change in the period. Astronomers continue to monitor this carefully, as any persistent change in pulsation behavior might carry information about changes in the star's interior structure. Betelgeuse is speaking to us in pulses. We are learning to listen. Let us explore what astronomers can learn from the pulsations of a star like Betelgeuse, because the rhythms of a star's variability are not merely interesting to observe. They are a window into its interior. The study of stellar oscillations, called asteroseismology, is analogous in some ways to seismology on Earth. Just as geologists study the propagation of earthquake waves through Earth's interior to map the planet's internal structure, astronomers study the oscillation patterns of stars to infer what lies beneath their visible surfaces. Different oscillation modes, different patterns of expansion and contraction, are sensitive to different regions of the stellar interior. The frequency and period of oscillations depend on properties like the density, temperature, and composition of the material through which they propagate. By carefully measuring these oscillations, astronomers can build models of what the star looks like on the inside. For Betelgeuse, asteroseismology is complicated by the star's extreme size and the dominance of turbulent convective motions. The giant convective cells that churn the star's outer layers make it difficult to isolate clean oscillation signals from the background noise of convection. Nevertheless, the oscillation data from Betelgeuse has contributed to our understanding of where the star currently sits in its evolutionary sequence. Combined with models of stellar evolution, the observed pulsation behavior is consistent with a star in the late stages of core carbon burning, or possibly already beyond that, in the phase of neon or oxygen burning. If this interpretation is correct, Betelgeuse may be closer to the end of its life than many earlier estimates suggested. Not necessarily in human terms. Even the late stages of nuclear burning in a massive star can last thousands to tens of thousands of years. But in stellar terms, the final chapters are being written. The pulsations are the heartbeat of a giant nearing rest. As we move into the later chapters of our journey tonight, let us explore the event that awaits Betelgeuse at the end of its life, and understand slowly and clearly what a supernova is and how it unfolds. Within the nested, layered interior of Betelgeuse, nuclear fusion is building ever heavier elements. Hydrogen fuses to helium, helium to carbon, carbon to neon and magnesium, neon to oxygen, oxygen to silicon, and silicon, at the extreme temperatures of the innermost core, fuses to iron. Iron is, in the context of stellar nuclear physics, a dead end. Fusing elements lighter than iron releases energy. It is this energy that has powered the star throughout its life. But fusing iron requires energy rather than releasing it. When the innermost core of a massive star becomes iron, fusion in that region simply stops. Gravity has been balanced throughout the star's life by the outward pressure of fusion energy. When fusion ceases in the iron core, that balance is broken. Gravity wins completely and catastrophically. The iron core, typically about the size and mass of Earth's moon or slightly larger, collapses in a fraction of a second. The outer material, no longer supported, follows falling inward at a significant fraction of the speed of light. The collapse releases an almost incomprehensible amount of gravitational energy, more energy in those fractions of a second than our sun will radiate in its entire 10 billion year lifetime. The collapsing core bounces become so dense that the fundamental particles it contains resist further compression, and a powerful shockwave propagates outward. That shockwave, energized by a torrent of neutrinos flooding outward from the newly formed neutron star at the center, tears through the star's outer layers. In a matter of hours to days, those outer layers, all the material Betelgeuse has accumulated over its millions of years of life, are expelled into space at thousands of kilometers per second. This is a core collapse supernova, the most energetic single event a star can experience. Consider, gently, what we will see from Earth when Betelgeuse eventually explodes. At its current distance of approximately 700 light-years, a supernova from Betelgeuse would be one of the most spectacular astronomical events visible to the naked eye in recorded human history. Astronomers estimate that Betelgeuse's supernova would reach an apparent magnitude of somewhere between -5 and -10, a range that spans from clearly brilliant to extraordinary. For comparison, the full moon reaches a magnitude of approximately -12.7. Venus, at its brightest, reaches about -4.9. A Betelgeuse supernova at magnitude -7 or 8 would be clearly visible in daylight. It would cast faint shadows at night. It would be the brightest object in the night sky by far for weeks, and possibly remain visible to the naked eye for months as the supernova remnant fades. The last supernova observable to the naked eye was SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way at a distance of approximately 160,000 light-years. It reached magnitude approximately 3, visible to the naked eye, but not dramatically bright. Betelgeuse is roughly 230 times closer than that event. The difference in apparent brightness would be enormous. A Betelgeuse supernova would be, without question, the most spectacular naked-eye astronomical event since the appearance of the supernova of 1006 AD, possibly since before recorded history. It would be visible to every human being on Earth with clear skies. It would dominate the night sky for weeks or months, and it would leave behind a supernova remnant, a glowing cloud of expanding gas that would be visible for thousands of years. Future generations will watch it fade across their lifetimes. Their children will study the glowing remnant through telescopes. As we continue contemplating the eventual end of Betelgeuse, let us turn to what will remain after the supernova, the extraordinary object that will be born from the star's death. When the outer layers of Betelgeuse are expelled in the supernova explosion, they will form an expanding shell of gas and dust, a supernova remnant illuminated from within by the energy of the explosion and by the radiation from the central remnant. This shell will expand outward into the surrounding space at thousands of kilometers per second, eventually merging with the interstellar medium and enriching it with the heavy elements forged in Betelgeuse's core. Some of those elements, carbon, oxygen, silicon, magnesium, iron, and many others, will eventually find their way into new molecular clouds. Those clouds will collapse into new stars. Those stars will form with planets. And some of those planets may carry, in their chemistry, atoms that were once inside Betelgeuse. The cycle continues. At the center of the supernova remnant, what remains of Betelgeuse's core will depend on how massive that core was at the moment of collapse. If the core was below approximately 3 solar masses, it will become a neutron star, an object roughly 20 kilometers across containing the mass of the Sun, composed almost entirely of neutrons packed to nuclear density. Neutron stars are among the most extreme objects in the known universe. A teaspoon of neutron star material would have a mass of approximately 1 billion tons. If the core was above approximately 3 solar masses, the collapse cannot be halted even by neutron degeneracy pressure. Gravity wins completely. The core collapses into a black hole. Current estimates suggest Betelgeuse's remnant core will likely form a neutron star, though the uncertainties in stellar evolution models leave some possibility of black hole formation. Either way, something extraordinary will be born from the death of the star we watch tonight. As we reach the heart of our question tonight, why scientists are so concerned about what Betelgeuse is doing right now, let us gather the threads we have been following and understand the full picture. The concern is not fear. It is not alarm. No responsible astronomer believes Betelgeuse poses any threat to Earth when it explodes. At 700 light-years, the radiation from its supernova will be far too diffuse to cause any meaningful harm to our planet or its inhabitants. The concern is of an entirely different character. It is the concern of people who know they are watching something that will happen only once, an extraordinary, unrepeatable cosmic event, and who want to be ready when it occurs. Betelgeuse is the closest red supergiant to Earth that is expected to undergo a core collapse supernova in the astronomically near term. The last supernova observed in our galaxy, or its close neighbors visible to the naked eye, was Kepler's supernova in 1604. Since then, the development of modern astronomy, astrophysics, and observational technology has transformed our ability to study these events. When Betelgeuse goes supernova, astronomers will have, for the first time in the modern era, a nearby supernova to study with every instrument available: radio telescopes, X-ray observatories, in space, neutrino detectors, deep underground, gravitational wave observatories, optical and infrared telescopes, on the ground and in space. The neutrino burst alone The flood of neutrinos released in the first seconds of core collapse will be detectable across enormous distances and will carry information about the innermost moments of the explosion that light cannot provide. SN 1987A gave us the first detected supernova neutrino signal from 160,000 light-years away. Betelgeuse is 230 times closer. The neutrino signal will be extraordinary. Scientists are watching Betelgeuse carefully because they want to be ready. Because some advance warning, however brief, could allow observatories worldwide to be pointed at exactly the right place, at exactly the right moment. This is a once-in-a-millennium opportunity, and it is coming. Let us explore one of the most fascinating aspects of scientific readiness for a Betelgeuse supernova, the fact that we may have a brief warning before the light of the explosion reaches us. When a massive star's core collapses in a supernova, it releases an enormous burst of neutrinos in the first seconds of the event. Neutrinos are subatomic particles with almost no mass and no electric charge. They interact with ordinary matter so weakly that they can pass through the entire Earth as though it barely existed. 1 trillion solar neutrinos pass through your body every second without affecting you in any way. This near-total non-interaction is precisely why neutrinos are so valuable as cosmic messengers. They escape from the core of the collapsing star almost instantaneously, within seconds of core collapse, while the shockwave that will eventually blow off the star's outer layers is still propagating outward. The supernova's light, the visible explosion, does not break through the star's surface for hours after core collapse. This means that neutrino detectors on Earth might detect the burst of neutrinos from a Betelgeuse supernova several hours before the visible explosion is seen. This is not merely theoretical. The neutrino burst from SN 1987A was detected by neutrino observatories on Earth approximately 3 hours before the light from the explosion arrived. Several neutrino observatories, including Super Kamiokande in Japan, IceCube in Antarctica, and others, are continuously monitoring for such a burst. A project called SNEWS, the Supernova Early Warning System, links these detectors into a network that can issue an automated alert to observatories worldwide within seconds of detecting a coincident neutrino burst from multiple instruments. If Betelgeuse goes supernova, astronomers around the world could receive hours of warning before the visible explosion. Hours in which to point every available telescope toward Orion, to calibrate instruments, to prepare detectors. Hours that could mean the difference between watching a supernova and truly studying one. As we continue our gentle exploration, let us address the question that many people ask when they hear about Betelgeuse: when will it actually explode? The honest answer is that we do not know, and the range of uncertainty is substantial. Current stellar evolution models suggest that Betelgeuse is in the late stages of its nuclear burning sequence, likely in the carbon burning phase or beyond, with silicon burning potentially still ahead. Each successive burning phase is shorter than the last. Hydrogen burning lasted millions of years, helium burning a few 100,000, carbon burning perhaps a few thousand years, neon burning perhaps a year, oxygen burning perhaps months, silicon burning perhaps days. If Betelgeuse is currently in the carbon burning phase, it might have thousands of years remaining. If it has already advanced to silicon burning, the end could come within years, or possibly already has, 700 years ago, and we will see the supernova imminently. The most widely cited range in the scientific literature suggests that Betelgeuse will likely go supernova sometime in the next 100,000 years. Some analyses, including one published in 2021, that attempted to interpret changes in Betelgeuse's pulsation behavior as evidence of its evolutionary state, suggested a timescale closer to tens of thousands of years, possibly shorter. But these are estimates with large uncertainties. The precise evolutionary state of a star's interior is not directly observable. It must be inferred from observable surface properties and compared against theoretical models. Those models are sophisticated and well tested, but they cannot predict the moment of a specific star's death with precision. It is possible, though considered unlikely by most astronomers, that Betelgeuse could go supernova within a human lifetime. It is also possible that it will continue to burn in its current state for tens of thousands of years before the final collapse. We watch, we wait, we remain ready. Deep within the question of when Betelgeuse will explode lies a related question. What, if anything, would we observe in the weeks, months, or years before the supernova that might serve as a warning? This is an area of active research and some uncertainty. Stellar evolution theory suggests that in the final stages before core collapse, a massive star might exhibit changes in its behavior, changes in its luminosity, its pulsation patterns, its mass loss rate. But whether these changes would be detectable and recognizable from Earth is not entirely clear. Some theoretical models suggest that in the months to years before core collapse, a red supergiant might show unusual dimming or brightening changes in its pulsation cycle or unusual brightening of its outer envelope as energy from the advanced nuclear burning escapes. But these predictions are uncertain, and the normal variability of a star like Betelgeuse, with its great dimming events, its complex pulsation cycles, its episodic mass loss makes distinguishing a genuine pre-supernova signal from ordinary variability very challenging. The neutrino signal we discussed detectable, perhaps hours before the visible explosion, remains the most reliable advance warning we currently have. But that warning is measured in hours, not months or years. This is why the continuous monitoring of Betelgeuse is so important. Astronomers are accumulating a long baseline of observations, detailed records of the star's brightness, color, pulsation, and spectral characteristics across years and decades. If the star begins to behave in genuinely unprecedented ways, ways that deviate significantly from everything previously recorded, that may be among the earliest observable warnings. For now, Betelgeuse is behaving as a red supergiant behaves variably, dramatically, and magnificently. It is not showing clear signs of imminent collapse, but it is being watched every night by observatories around the world. As we move toward the closing chapters of our journey tonight, let us pause and appreciate something that science alone cannot fully capture: the place Betelgeuse has held in the human imagination across the centuries. The constellation Orion is among the most universally recognized patterns in the night sky. It is visible from virtually every inhabited location on Earth, from the high Arctic in winter to the southern hemisphere's summer evenings. Its distinctive shape, the belt of three aligned stars, the surrounding bright stars marking the shoulders and feet of a hunter, has been recognized and named by cultures across the globe. Ancient Egyptian astronomers associated the belt of Orion with Osiris, the god of death and resurrection. Ancient Greek mythology placed Orion as a great hunter, his constellation rising to prominence in winter evenings. Medieval Arab astronomers, who gave us the names of many of the brightest stars, called the reddish star at Orion's shoulder, Ibt al-Jawza, meaning shoulder of the central one, which through linguistic transformation over centuries became Betelgeuse. In the cultures of indigenous peoples across multiple continents, the Orion constellation holds significance as hunters, as seasons, as navigational markers in the night sky. The stars that compose Orion have been watched, named, and storied by human beings for as long as human beings have had stories to tell. And always, that warm reddish star at the shoulder has been among the most recognizable. Not the sharpest, not the most precisely fixed in position, but somehow the most characterful, carrying a warmth and a presence that the blue-white stars nearby lack. For every generation of humans who has ever looked up at a winter sky, Betelgeuse has been there, patient, ancient, glowing softly in the dark. When it explodes, whenever that occurs, it will be the end of something that every human culture in history has shared. A familiar star, gone, and the beginning of something new. Let us consider, as we near the end of our journey together, what the careful watching of a single star like Betelgeuse reveals about the practice of science and about the relationship between human curiosity and the cosmos. Betelgeuse has been continuously monitored by professional astronomers for decades. The American Association of Variable Star Observers, AAVSO, maintains records of Betelgeuse's brightness stretching back over a century, compiled from observations by both professional and amateur astronomers around the world. This long baseline of data is invaluable. It provides the context within which any unusual behavior can be recognized and assessed. The great dimming of 2019 and 2020 would have been far less scientifically interpretable without that century of prior observation. It was precisely because astronomers knew how Betelgeuse normally behaved, its typical range of variability, its pulsation cycles, its historical brightness, that the dimming stood out as significant. This is how science works, not in dramatic leaps from ignorance to understanding, but in the patient accumulation of observation over time, in the slow building of a baseline that makes anomalies visible, in the willingness to keep watching, even when nothing seems to be happening, because something might. There is a kind of devotion in this, a quiet, sustained attention that is, in its way, a form of care. Astronomers and dedicated amateur observers around the world turn their instruments toward Betelgeuse night after night, recording its brightness, noting its color, watching for anything that might signal a change. They do not know when the supernova will come. They may not live to see it. Their children may not live to see it. And yet they watch, because someone must. Because the opportunity to observe a nearby supernova in the modern era, with all the instruments and understanding we now possess, is one of the most extraordinary scientific opportunities imaginable. And because Betelgeuse deserves witnesses. And so we arrive, gently and without hurry, at the end of our journey tonight. We have traveled far with Betelgeuse. We have learned what it is, a red supergiant of extraordinary size, puffed to dimensions that could swallow the inner solar system, burning through the final stages of a stellar life that began roughly 10 million years ago. We have explored its great dimming, that remarkable episode of dust and cooling that dimmed one of the sky's most familiar stars and briefly, wonderfully, reminded the world to look up. We have sat with the complex, churning activity of its surface, those continent-sized convective cells rising and falling, ejecting material into space, pulsing in rhythms that carry information about the star's deepest interior. We have contemplated the layered, onion-like structure of its interior, where successive shells of nuclear fuel burn at ever-increasing temperatures, building ever heavier elements, marching step by step toward the iron core that will one day bring everything to a halt. And we have considered what happens then. The core collapse, the supernova, the extraordinary brightness that will transform the night sky for months, the expanding remnant that will glow for thousands of years. Down to now, the neutron star or black hole born from the ashes of a giant. We have asked why scientists watch so carefully and found that the answer is not fear but readiness. The eagerness of people who understand that they are living through a period when the tools and knowledge exist to observe a nearby supernova in extraordinary detail, and who want to be prepared when that moment comes. And we have held Betelgeuse, in its human context, as a star that has been part of the human sky for as long as humanity has had a sky to share, a familiar presence in winter evenings, a warm light among the cold blue-white of Orion's other stars. Tonight, when the sky is clear, you might look for it, not with urgency, not with alarm, simply with the quiet awareness of what you are seeing. A star 700 light-years away, 700 light-years, an almost incomprehensible distance across which its light has traveled for centuries to reach your eyes. A star in the final chapters of its life, measured in cosmic time. A star that has built, in its core, the heavy elements that will one day seed new solar systems. A star that is, in the most literal sense, part of the story that led to you. The atoms in your body, the carbon, oxygen, nitrogen, the iron carrying oxygen through your blood right now, were made in stars, not necessarily in Betelgeuse, but in stars like it, in the supernovae that preceded our sun's formation, in the cosmic cycle of stellar birth, life, death, and rebirth that has been running since the universe's first stars lit up more than 13 billion years ago. Betelgeuse will die. It will explode with extraordinary brilliance. It will scatter its contents across light years of space, enriching the interstellar medium with the products of its long nuclear burning. From that material, in the fullness of time, new stars will form, new planets will coalesce, new chemistry will emerge, And somewhere in that future, perhaps something will look up at a night sky and see a warm, familiar star. That is not a small thing. That is the universe continuing its work. Tonight, let Betelgeuse rest in your mind as it rests in the sky, patient, ancient, magnificent, and unhurried. Let its warm light be a reminder that the cosmos is in no rush, that the grandest events unfold on timescales that dwarf anything we can measure in a human life, that there is time, there has always been time. The star at the shoulder of Orion has been there for every winter sky in human memory. It will be there tonight, and tomorrow night, and for many, many nights to come. Rest now in the knowledge of that continuity, in the quiet permanence of a sky that has been watched by human eyes for thousands of generations and will be watched for thousands more. The universe does not need your vigilance tonight. It has astronomers for that. Thank you for exploring with us tonight. May your rest be as vast and patient as the life of a star.